Let's take a fairly in-depth look at the graphs of the three major trig functions that we're going to be working with, sine, cosine, and tangent. Specifically, let's talk about translations or phase shifts when we're talking about these trig functions. Let's take a close look at the graph of the sine function. Remember, we can, using radian angle measure, we can go old school and we can put those values into the sine function machine and find the corresponding outputs of those points. When the angle measure is 0 for sine, we know that the y-coordinate to the point on the unit circle is 0. That leads to this point, the point of origin, on the graph of the sine function. Furthermore, if we put pi over 2 radians in the sine function, we're going to get a sine value of 1. That's why at an input value of pi over 2, x values are radian angle measure, we are going to get an output, a y output, these are xy points, of 1. When we have an input of pi in the sine function, we get an output of 0. The input of 3 pi over 2 gives us an output, a y value, of -1. And to finish off one full period of the sine function, at 2 pi, we have an output value of 0. The sine of 2 pi is 0. There is one full rotation around the unit circle. That's why a period of sine is 2 pi. And there is one representative piece of the graph of the sine function that covers one period. From 2 pi to 4 pi, sine continues to look exactly like that. This is the parent sine function graph. Now, we can manipulate that parent function. We can translate it horizontally, vertically. We can reflect it over the x-axis, over the y-axis. We can do lots of things to this function to change from the parent function, but make sure you're comfortable graphing the parent sine function, the parent cosine function, and the parent tangent function. For tangent, just that one little piece around the origin like we first talked about. But we can look at the analytic function rule for these functions, and we can determine if there has been, just by looking analytically, we can determine if there has been some sort of translation, and we can figure out specifically what translation has gone on. Just like we talked about this parent function, and we talked about those kinds of translations. I'll even go so far as to put something like that on there. We know that that is a horizontal change. That is a vertical change. That is a stretch. Just by looking at the analytic function rule and seeing the difference from the parent function to one that has been translated somewhere in the plane, we can talk about what translations have gone on. We can do the same thing with sine, cosine, and tangent. Here is the parent cosine function. If our angle measure is 0, the cosine of 0 is 1. We get that from the unit circle. So at an input value of 0, the output on the cosine function is 1. At pi over 2, cosine is 0. That's the coordinate of this point. At pi, cosine is -1. At 3 pi over 2, cosine is 0. And at 2 pi, we've come back up to the cosine of 2 pi is 1. So this little stretch right here should be red as well. I'm not sure what happened there. So one full period along the x-axis, again, angle measure, radian angle measure, 1 full period of the parent cosine function looks like this. And from that point on, from 2 pi to 4 pi, the graph just repeats. That's why we call these periodic functions. Let's take a look at changes, stretches, compresses, vertical translations, horizontal translations. The first thing I want to talk about is a stretch or a compress. Remember, if we had a parent function and we put some sort of value greater than 1 in front of that parent function, that was a stretch. And that makes sense. This function, whatever its outputs are, this function is going to have outputs everywhere that are 3 times bigger. This function is going to have outputs everywhere. If we had just in general, this function is going to have outputs everywhere that are half as big as the parent function. That's why this looks like a compress or a shrinking. So is the same thing happening for sine and cosine? Or is that only true for non-trig functions? Well, let's look. The red graph here is y equals 2 sine of x. Notice on this sine function, the period is still 2 pi. We still start at 0. We still have a 0 at pi. We still have a 0 at 2 pi. But instead of having an output of 1, there's 1, there's 2, 3, and 4. Instead of having an output of 1 at pi over 2, which is what the parent sine function does, this red function has an output of 2. And additionally, the sine function has an output of -1 at 3 pi over 2, but this red function has an output of -2. So it turns out that the coefficient in front of some value a, in front of our trig function, does stretch, or notice here, does compress. There's 1/2, there's -1/2. It does stretch or compress our parent trig functions just like it does all other functions. The only difference when we get into trig functions is that instead of just calling that a constant, and instead of just calling that a stretch or a compress, in trigonometry those coefficients or translations have been given different names than we're used to. So the coefficient in front of the entire function, if there's a real number value, any real number, can be bigger than 1, can be between 0 and 1, can even be a negative number. That's called the amplitude. For those of you that haven't had trig, that may be a new term for you. That's perfectly fine, not a problem. The amplitude is the measure that the outputs are stretched. The negative is not part of the amplitude. The amplitude is just a positive real number measure that tells you how far above for a maximum or how far below for a minimum that the outputs of that parent function have been stretched and or compressed. So the amplitude tells you about stretching and compressing. It shrinks or stretches vertically the outputs of your function. So if I have y equals 3 times the cosine of x, I should be able to start with my parent cosine function and know that I'm still going to have the same zeros. I'm still going to have the same input angle measures where my maximums and my minimums occur. It just turns out that my maximums and my minimums are going to be stretched if it's larger than 1, or compressed if it's between 0 and 1. So I ought to be able, instead of coming up with a table of values, which I shouldn't have to do at this point, I should be able to start from the graph of my parent function and recognize that the 3 in front of the cosine function means that my maximums and minimums are going to be 3 units away from that horizontal axis. So I want you to be able to make changes on the known graph of the parent function. It's why I want you to know the graphs of your parent functions. So just like we did before, when we talked about what happens to the graph of a parent function when we feed it a negative input value, and or what happens to the graph of a parent function if we place a negative out front. This, in essence, was a reflection over the x-axis, because all positive output values became negative, and all negative output values were now a negative negative or a positive. So it just flipped or reflected the graph of that function over the x-axis. In the same way, all input values that were negative now are positive, or that were positive now are negative. So this was a reflection over the y-axis. If our function was even, we really wouldn't see any appreciable change in the graph of our function. So the period of our trig functions can change. We have parent functions for sine and for cosine, and we know the period for those two parent functions is 2 pi. In other words, the graph repeats every 2 pi along the real input x variable horizontal axis. For tangent, we've already discussed that we know the period is pi. It repeats itself every pi. So if we change the value inside of the function, if we go through those angle measures twice as fast or half as fast as we do in the parent functions, shouldn't that change the graph? Yes, because it changes the period. It says that instead of the parent sine function taking 2 pi radians to go completely through one, that's the red function here, one full period going all the way around the unit circle, we're going around the unit circle twice as fast. So we're going to go through 2 maximums and 2 minimums in the time that the parent function is just going to have 1 maximum and 1 minimum. That's going to give us more zeros. So yes, anything that's happening inside, anything that is affecting how quickly we're traveling around that unit circle and going from 0 to 2 pi is going to affect the period for the graph of a baby function based on one of our trig parent functions that we know. Here specifically is how that affectation is going to take place. We talked about A being the amplitude. Now, any coefficient to your independent variable is going to affect your period. So you need to be aware of that when you're graphing sine and cosine functions.